We're going to talk now about confidence intervals, which quite frankly I find to be the most enjoying part of this course. We're estimating mu. Okay, so let's start out, and I'm going to talk about something we need to give a name to. Okay, this is the beta tail. Okay, take z sub beta and mark it here. Here it's just by coincidence put it at 2, but you know, it's everywhere along here. The important thing is that beyond this point, for z beyond this point, the probability of that is beta, you know, whatever beta might be, and this is a number then we would have to find out some way. Okay, the way we find it is by using what's called a t-table or a t-inverse table. And what you do, you use your subscript. In this case, beta is equal to 0.025. You go up to that column on your table and then run all the way to the bottom of it and pick off that number, which the arrowhead kind of obscures it, but it's 1.960. Okay. Okay. For if I were going to put if my beta were equal to 0.2, it would be my z sub beta would be equal to 0.842. Okay. So this is the idea. We have some population data out there somewhere, and we draw a sample from it. Okay. Now, I know, because I'm the one that set this up, that the real mean of the population is 1.55. But we take the mean of this sample, and it's 1.43. And as you can see there, it's wrong. Okay, and quite frankly, it is always going to be wrong. There's probability 0 that this will ever be exactly right when we do it. Okay, but this is statistics, and so what we need to do, analyze this. The sample mean is close to the population mean, but they are not the same, so we must allow for error. And the amount of error we allow for is called the margin of error. Okay, and we denote it by E. Okay, so here we have set up this is okay, mu. Okay, and we allow a margin of error mu minus E down here, mu plus E down here. We draw a sample. Okay, X bar. Okay, and see if we draw it from here and it lands here, it's okay, and it lands here, it's okay, because that's within the margin of error we set from ourselves. But if we draw it and it lands here, okay, that's wrong, because it's beyond the margin of error we decided to allow for ourselves. Okay, so this is the way we're thinking. Okay, if we just use X bar, we're going to be wrong. Okay, so we set ourselves a margin of error. Okay, say we're going to be between here and here, but even doing that, there's still a probability that we're going to be wrong. Okay, even more than the margin of error, and that amount is this area under these two tails. That area is going to be the probability that we're wrong even beyond the margin of error. Okay, and we call that the sum of this alpha. Okay, alpha we want to be small because it's the probability that we're wrong beyond the margin of error. We want to keep that small. Now 1 minus alpha is called the level of confidence. Okay, we want to phrase things in a positive way, and so level of confidence will be something that we're going to want to try to keep close to 100%, okay? But the alpha itself is called the significance. Okay, and so let's do some calculations here. So say we've got this x bar, and that everything, what is the probability that it's right, that it's within our margin of error? Okay, well, to calculate we have to do a z-score, so we subtract mu from everything first, and then we divide everything by the standard error of the mean. Okay, and so this gives us, okay, the probability that the absolute value of our z-score is less than e over our standard error. Okay, and this okay is our level of confidence. Okay, let's flip that around. If we look at the complement, okay, the probability that we're bigger than this, okay, that's going to be alpha. Well, this right here, this is just z, so the probability that z is the absolute value of z is bigger than this e over the standard error of the mean is alpha. Well, by the symmetric properties of the normal curve, I can take off that absolute value at the price of dividing my sigma by 2, and so I can say that this e over x sigma x bar is equal to my z sub alpha over 2, right? So this is exactly the point at which the probability beyond that point is alpha over 2. This is the value of my alpha over 2 tail. Okay, so, and remember, I'm dividing the alpha over 2. I'm not dividing the z by 2. I'm dividing the alpha by 2. Okay, so I take this guy and I say, okay, my sigma x bar is actually sigma sub x divided by the square root of n, and then I multiply both sides by that, and so what do I have here? I have a formula for my margin of error. Okay, let's take a look at it. Okay, what is my margin of error? Okay, it's my standard error of the mean multiplied by this fudge factor. It's a it's something, okay, the standard error of the mean, this is the basic thing, but to get this is the way I get control over it. I have this multiplier out front. Multiply, make it more often than not bigger to handle the error. Okay, so let's see how this works out in a problem. So if we have x is a normally distributed random variable with a standard deviation equal to 4.2 and a sample of size 36 is taken, what is the margin of error if we have a confidence level of 90%? Okay, so write this stuff down real quick. You might want to pause so you can write it down, because I'm going to the next slide. And my sigma 4.2, my sample size 36, my confidence level 90%, which I write at 0.9. This gives me alpha equal to 0.10, alpha over 2 equals to 0.5. I do a table lookup to get my z sub alpha, go to my t-table, 1.645. And then we feed the formula. Okay, we've got our formula, z sub e equals z sub alpha over 2, sigma over the square root of n. Well, I plug in the stuff and it rolls it out like so. Now, in practice, what I'm going to want to do is to round this margin of error off basically to the same level that my x bar and my sigma are, so that I would probably wind up rounding it off to 1.2, but we'll do some more stuff here. Example 2. Bertram Bottlebutt has collected 49 specimens of the rare flesh-eating strip pit newt and measured their left fangs. He obtains an average of 10.2 centimeters with a standard deviation of 4.1 centimeters. Obtain a 95% confidence interval for fang length in this species. Okay, no newts were harmed during the conduction of this experiment. Okay, so we've got a sample of 49. We took X bar, 10.2. We've got standard deviation 4.9. It was a 95% confidence interval, so that'll give me alpha equal to 0.5. I divide that by 2, so I'll be looking up my z sub 0.025. We do that, and it's 1.96, and then we feed our formula for the margin of error, 1.9, our fudge factor times our standard error, 1.372. Okay, we only got 1 decimal of accuracy here, so it's just stupid to pretend that we have more. It's not stupid, it's dishonest. So we only have 1 decimal of accuracy here, and so our initial estimate, which was the X bar, we know it's wrong, so it might be a little low, so you add 1.6 and get 11.6. It might be a little high, so you subtract 1.4 and get 8.8, and so mu is somewhere between 8.8 and 11.6 with 95% confidence. Okay. Example 3. Shirley U. Jest, local eccentric, collected 64 fecal samples from her front lawn which were left by neighborhood dogs. These average 5.5 kilograms with a standard deviation of 3.2 kilograms. And by the way, this is hilarious if you know the metric system. Determine a 98% confidence interval for the average specimen size. Okay. So sample size of 64, average 5.5, sample standard deviation 3.2, 98% confidence means that alpha is equal to 0.02, 2%. Alpha over 2 is 0.01. Do the table lookup for z sub 0.01, it's 2.326. Okay, and feed the formula, our fudge factor times the standard error of the mean. We do the math. We only have 1 decimal on the X bar, so we round this to 0.9. Okay, our initial estimate, the X bar 5.5, it could be too small, so you add the 0.9. Could be too big, you subtract the 0.9, and so we know sigma is between 4.6 and 6.4 with 98% confidence.